Hello everyone. In this video, I'll discuss the basics of neural network, development of different models over time, how to vectorize the calculations, and in the end, we'll construct a feed-forward neural network in Python. So as we all know, a neural network is trying to mimic the functions of neurons in the human brain. The first computational model of a neuron was proposed by McCulloch and Pitts in 1943, and this is how the model looks like. So the model says that it takes excitatory inputs x1, x2, x3 and so on. So the excitatory inputs are binary inputs. So what it will take the input and it will add up the inputs. So that is what the g of x is doing. As you can see, g of x is equal to summation of all the excitatory inputs. Now there is another type of input called the inhibitory input. So this inhibitory input has the veto power in the MCP model. So what this means is that, okay, let's see the model first. So after taking the input, this f of x will produce an output, and again it will produce a binary output 1 if g of x is greater than a certain threshold and there is no inhibition. Otherwise it will produce 0. So what this means is, once g of x has added all the excitatory inputs, and if there is no inhibitory input on, so this inhibitory input has a veto power. If it is on, the model will always produce 0. But if we say that the inhibitory input is off, or you can say 0, then the g of x will add all the inputs, and then f of x will compare if the sum addition is greater than a certain threshold. If yes, and if there is no inhibition, it will produce 1, otherwise 0. So we can see the working of this model, MCP model here. x1 is 0, x2 is 0, and if there is no inhibition, then 0 plus 0 is 0, and this 0 is less than the threshold set equal to 1, therefore the output will be 0. 0 plus 1, 1, 1 is equal to 1, which is the threshold, therefore the output is 1. Similarly, therefore you can see the output will be 1 for all the three cases. Let's see for AND gate. 0 plus 0 is 0, which is less than 2, therefore the output is 0. Here the output will be 0 for 3 out of 4 cases. Now based on the MCP model, Frank Rosenblatt gave the computational model for a perceptron, which is the basis of the current day neural networks. Now what is different about this model, Frank Rosenblatt's perceptron, than McCulloch and Pitts, is that the inputs have a weight attached to them. There is one more term which we'll study later in backpropagation, and that term gives us a way to change the weights of the inputs based on a learning rate and the difference in inputs. So we'll study more about that term when we study backpropagation. So one important thing is that this concept of having certain weights attached to the inputs, as well as the way to change the weights based on the learning rate, these two concepts were proposed by Hebb's law. So we are not going to study Hebb's law. So after McCulloch and Pitts, there was one more model, Hebb's law, and after that, after too many years, then in 1980s something, Frank Rosenblatt gave the concept of perceptron. So what is different about this model is that I told you, like, as the inputs have certain weights, but again the g of x function will produce the sum product of the inputs and weights, that is wi multiplied by xi, and the summation of all these terms. Once g of x has produced all these things, f of x again will decide if g of x is greater than a threshold. If yes, then it will produce 1. If no, then it will produce 0. Here there is no inhibitory input. As you can see, removal of absolute inhibitory synapses. So this threshold kind of works as a inhibitory input. So based on the two models, let's develop a general framework. So the general framework is, a neuron will accept inputs which will have certain weights attached to them. it will produce the sum product of the input, it will add a bias. Now why do we add the bias? There are different advantages of adding the bias, but one advantage is that it will shift the activation function. Now what is activation function, we'll see, but for now you can just assume that adding b is advantageous for our purpose. So once g of x has produced the sum product of the inputs and weights, and we add a bias to it, then this activation function will take the output of g of x. And so there are two things which we can use this model for. Either we can use it for classification or we can use it for regression. So suppose if we are using it for classification, then and that too for particularly for binary classification, then we can see that this activation function will again use the output of g of x, and based on what is the function, it will convert it to some different value, and if that value is greater than certain threshold, we'll get the answer as 1, otherwise 0. If the problem is of regression, then f of x, whatever the function is, this function will convert the output of g of x, and that output will be y hat, or you can say the predicted value for the regression. This is the general setup or general framework for the neural network model. Now as we know that we will construct the neural networks in matrix formulation. So let's see how to start with the easiest step. So we can see that in the process of neural network, we are multiplying inputs with the weights and adding them up, and then adding the bias term. So there is a way to vectorize this. We can simply take the dot product of the weights vector and the input vector. As you can see, if w1 w till wn is a weight vector and x is the input vector, we can simply take the dot product and we'll get the sum product. Now coming to the matrix formulation for feed forward neural network. Now what we studied till now or till this point was just one neuron. But okay, let's look at just one neuron. What this is doing is, this is a neuron, it is accepting x1, x2, x3. These inputs are multiplied by their weights and then added, and the bias term is added, and this f of x will work on the output of g of x to produce a binary output. Suppose we are considering the framework for classification, so then we'll have 0 or 1. Okay, remember one thing here, when I say summation of from I is equal to 1 till n xi multiplied by wi, this n refers to the number of features in a data set. Usually we use n for number of observations, but don't get confused. This n here refers to the number of features or number of input parameters. Okay, so coming back to this, g of x, as I told you, produces the sum product. Now f of x acts on the output. Now f of x, as I told you, this f of x or f of z is called as activation function. And why is this important in our study? So activation function is very important because we want to introduce non-linearity in the model. So one of the drawbacks of these two models, the McCulloch and Pitts model and Frank Rosenberg's model, is that just one single neuron can work for OR gate and AND gate, but they don't work for XOR gate. So if we want to create a model which will particularly solve the case for XOR, we need to have more than one layers. So, and if we have more than one layers, and if we don't have an activation function, then it will just be a linear summation of all the weights, and there will be no non-linearity. So that is the main function of having activation function. So another advantage of having an activation function is when we want to constrain the outputs. Suppose we want the outputs in the range of 0 to 1, because like in the case of classification, we want the answer to be between 0 to 1, because they will represent probabilities. So that is another function. There are many other functions, there are many other advantages of having an activation function. So okay, looking at examples, sigmoid is a kind of activation function which takes x and it gives out value between 0 and 1. Similarly, tan h is equal to e to the power x minus e to the power minus x, the whole divided by e to the power x plus e to the power minus x. And this ReLU is a very important activation function, and this has very good properties, such as it removes the property of vanishing gradients, so that's why it is quite popular in deep learning community. And another variant of this is leaky ReLU. So what is ReLU is, it will take the maximum of 0 or x. Now one more thing, so usually there is one more activation function, softmax. So usually in the hidden layer, we'll see what is a hidden layer. Okay, so in the hidden layer we use ReLU activation function, and in the output layer we use softmax or sigmoid depending on our task at hand. So okay, let's look at this multi-layer neural network. Sorry, not multi-layer, one hidden layer neural network. Okay, yeah, one more important thing regarding the naming of this network. I call it one hidden layer neural network. Some people call it two layer neural network because they consider output layer as a layer, output neuron as a layer. And some people call it three layer if you consider this inputs also as an input layer. So right now we will just stick with one hidden layer neural network. Now consider a problem. So how will you approach this problem? So what's happening is, suppose our data set, suppose these are the inputs x1, x2, x3, and these are two perceptrons. Again, what g of x will do is, it will take the inputs and there will be some weights attached to these inputs. It will produce the sum product, a bias will get added, and the activation function will act on the output of g of x. The same thing will happen in the second neuron. Again, it will take inputs, all the inputs. Okay, so remember what this kind of neural network is called as fully connected neural network. That means all the inputs are going to all the neurons. If there was one more neuron, then again all the inputs would go to that neuron as well. So it doesn't matter how many neurons are there, the inputs will go to every neuron. So what does that mean? That means if g of x has to produce the sum product, g of x needs to have the weights for all the inputs. Similarly, g of x for this neuron will also need to have the inputs for will also need to have the weights associated with all the inputs. So what does that mean is, like, every neuron will have the same number of weights as the number of input features. Okay, and again each neuron, and again a bias will be added in each neuron. The activation function will also act on the output of the previous of g of x. Okay, let's look at this example. Consider a real world problem of determining whether a person will get heart attack. So suppose our data set looks like this: age 37, cholesterol 200, and body fat 20. So this is x1 input, x2, and this is x3 input. And heart attack is a binary variable. It will be either 0 or 1. And suppose we have m observations. Suppose we have m observations and 3 features. This is what a data set looks like. Now let's study the process. Each observation will be passed as input to all the neurons. I just told you, each observation, this is one observation, this will be passed as input to all the neurons collectively. This means each neuron will produce some product of weights and inputs, and a bias will be added to each sum product in each neuron. Second, the sum product will be passed through the activation function. Okay, so the sum product which g of x generates, this will be passed to the activation function here also for each neuron in the hidden layer. Hidden layers can have activation functions such as ReLU, leaky ReLU, whereas output layer can have the following activation functions such as sigmoid for binary classification, identity function for regression, and softmax for multi-level classification. Now coming back to the procedure, after getting the output from hidden layer activation functions, okay, remember this g of x will be a value, this will get converted into f of like the output of this function, and the output of this function is again passed as input to the output neuron, and again this input will have some weight attached to it, again this input will have some weight attached to it, and those, that means the output layer will have two weights for each input. The sum product will be passed through the activation function of output layer. Okay, sorry, again the output neuron will perform the sum product. Okay, so we had covered this. After getting the output from hidden layer activation functions, this output is then used as input to the last neuron. Again the output neuron will perform sum product of its input and weight. Bias will be added. Okay, remember there is a bias term in the output last neuron as well. The sum product will be passed to the activation function of the output layer, and final answer will be between 0 and 1. Okay, right now we, just to understand, we are learning the example of classification, so that's why we are using sigmoid activation function here, and the output will be between 0 and 1. Here the final answer will be between 0 and 1, but again this is a probability, and if like the data set which we have, for a particular input we have answer as 1, so what we can do is, after getting the answer between 0 and 1, we can do this. If the answer is more than 0.5, we can assign it 0, and if it is less than 0.5, we can assign it, if it is more than 0.5, we'll assign it 1, and if it is less than 0.5, we'll assign it 0. So what the process which I described till now, this process is just for one observation, which is the first row, and we have to do this for all the observations in the data set. So let's see how this actually looks like and see if we can vectorize this calculation. Okay, I have done this just for 2 neurons and just for the first observation. Okay, this is how my data set looks like. x1, x2, x3 are the 3 inputs, and we have m observations. Similarly, we have m labels. Okay, so here I have written everything in a matrix structure. This is my data set, and this is the structure of my hidden layer. So W11, W12, W13, these are the weights associated with the inputs for the first neuron. Similarly, W21, W22, W23, these are the weights associated with my inputs for the second neuron. So performing the matrix calculation, this row along with this column, we get x11, W11 here, plus x12, W12 here, plus x13, W13 here. Similarly, we'll go on doing this for the second observation, for the third observation, and so on till m observations. So the first column which you see is the sum product. Again, you can cross check, this matrix is of the dimension m cross 3, and the weight matrix of the neuron is of dimension 3 cross 2. Therefore, after multiplication, it will be of dimension m cross 2. So that means we will have m rows and 2 columns. So this, the first column which you see, which you will get after multiplying this 2 matrices, is the sum product of the first neuron. That means what's happening is, if all the inputs are passed through the first neuron, this is what we will get. If all the inputs are passed through the first neuron, this column is what we will get. Similarly, if all the inputs are passed through the second neuron, this column is what we will get. And again, if you remember, we are supposed to add biases to it. So we have to add B1 bias, which is the bias for this neuron, to all the values. Similarly, we have to add bias for this neuron to all the sum products. So this is how you'll do it, adding bias to each sum product. So x1 w1, x2 w2, x3 w3 plus b1. This is what you are seeing it here. xm1 w11, xm2 w12, xm3 w13 plus b1. Similarly, addition of this plus this. So again you will get, this was m by 2 and this is again m by 2, so you will get m by 2. Now after that we have, so this matrix, what is this matrix? This matrix is this final matrix m by 2. So I have just written sum product, but you should understand that this sum product also includes bias. So sum product of the first observation for the first neuron, similarly sum product for the first neuron for the mth observation. As I told you, like this, the first column represents all the outputs of the first neuron and the second column represents all the outputs of the second neuron. Okay, now coming to the second step, this f of x is the activation function, and we just discussed that we used ReLU for this activation function of the hidden layer. So if we apply ReLU of sum product of the first observation of the first neuron, so nothing, I am just simply applying ReLU on all of this. So, because the ReLU is the same, like it will choose the maximum of between 0 and the input. So we'll have after this step we'll have either 0 or the maximum value between 0 and the x or the input. Now after getting the ReLU, after applying the activation function on the output of this, we'll have, this is the output after applying the activation function. Now again this will be used as input to the output neuron. Again the output of this activation function will be used as input to this neuron. So what's happening is, again in this part of the neuron, the inputs will be multiplied by their weights and a bias will be added. So that's what is happening. So the inputs, what's happening is, this ReLU sp1 will be the input from this, ReLU sp2 will be the input from this, and this will have certain weight w1 w2 associated with it, but it is for the third neutron. That's why there will be a, if you just perform matrix multiplication, you can see that this is m cross 2 and this is 2 cross 1. So the final dimension will be m cross 1, which is consistent with our formation, or you can say the framework, because the output is m comma 1 or m by 1. Thus what we can see is, if we try to generalize the matrix, formulation can be written as, dataset dimension is m by n. M is the number of observations and n is the number of features. Here n, for our case, for the case of predicting whether a person will have heart attack, the output is binary 0, 1, and we have three inputs, age, cholesterol, and cholesterol and body fat. Okay, so yeah, the dataset dimension is of m by n. The weight matrix associated with the two neurons is n by this is not 0, this is just O. So O can, here in our case, what is O? O is 2. O, if there were 3 neurons, then this would have been 3. So n by O means n is the number of inputs, like this, and O is the number of neurons in the hidden layer, and m cross 1 is the number of, like, output vector. However, remember one thing, this is the convention used by us. However, in the field of machine learning, the widely used convention is, the inputs are not passed m by n, but rather inputs are sent as n by m dimension. Like that means the transpose of this. That means you have to take the transpose of all the matrices and the answer will still be consistent, but it's just that it's up to you. You can either use this convention or you can use this convention.